Oh, hi there. Thanks so much for showing up for your learning. It's Mr. Jennings, and we are looking today at Trigonometric Equations, number 4.4. Now, I'm very sorry that I wasn't able to show up for your learning today. I want to be there, but instead I'm here at home. I've got my coffee. It's the morning, so the coffee is important. And I've also got a cupcake. This is not a flex. Okay, this is me demonstrating that you should put nice things after the things that you need to do to encourage yourself to do the things you need to do. Once you've solved some hard problems, you should reward yourself. For me, these problems are their own reward. I love this stuff, but you want to do this right. Okay, so let's take a look at what we're doing today. We're going to need our cast rule. We're going to need related acute angles. We're going to use our special triangles. We're going to be also using the cosine inverse function or the sine inverse to solve approximate solutions, and we're going to be using things like factoring, even the quadratic formula to find exact solutions. Now, get your calculator into radian mode. We're not in degree mode anymore because we're grade 12s, and I just wanted to take a little tour of Desmos and show you how to get Desmos set up for radian mode. Now, Desmos is natively in radians. You can see there, it's in radians. So you have to toggle it to degrees, but you can actually have the scale show up like I have it there by just putting that in pi. How do you get pi there? Just write pi up. How do you get pi there? You go in here, boop, boop, write pi, pi. That's it. Now my scale is beautifully in pi, you can see. Great, beautiful. Okay, let's keep going. So, cast rule. Nothing particularly surprising here. We've seen this multiple times. Just wanted to do a brief review. Like cosine is positive all in this range because cosine is related to the x value of those triangles that we draw. Like if this is positive, then cosine is positive. If you're looking at something like up here, where sine is positive all the way up there, well, that's because if I draw one of these triangles over here, the y component, which is the opposite side, that's positive, so sine is positive. And then y is tangent, positive down here, as well as up here. Like, why does it have this, like, this shape? It's because the ratio of the two sides is the same. So even if I draw this triangle down here, the ratio of this negative thing to that negative thing, the ratio of two negatives would be a positive ratio. So that's why it's positive there and up here where they're both positive. And then looking at related angles and terminal angles, like you would just want to have this stuff ready to go. So if you think about something like your 30, 60, 90 triangle, which I know you think about a lot, here's your 30 degree or your pi by 6. Here's your 60 degree or your pi by 3. And here's your right angle or your pi by 2. But most people just write a right angle on that. Okay? We know that this side is 2, this side is 1, and this side is root 3. So if I flip that around and draw it over here, well, this would be 1, and this would be negative root 3, and this would be 2. So to work with something like 150 degrees, you just imagine your special triangle just kind of flipped around and moved over here, and then the related acute angle tells you the value of all those ratios, and just using x and y will tell you which one of those are positive and negative. Similarly, if I were working down here, I just like imagine my special triangle there. This is negative 1, this is negative root 3. So my tangent to the value of tangent for 210. So tan 210 will be equal to opposite over adjacent, but it's cast rule. So of course that's positive. And you know it's positive because a negative divided by a negative is a positive. That's what we do with the related acute angles. This is all they're for. And a quick review. Okay, the range and domain of our trigonometric functions, sine and cosine, they go off to infinity in both directions. Okay, but they have a maximum and minimum value of 1. Tangent, on the other hand, has no max nor min. It can go off to infinity in both directions. And it goes out to infinity in both directions too for x, but it does have some vertical asymptotes. And it has vertical asymptotes over here. Let me show you. So if we just turn that one off, we'll turn that one off for now, that's for later. Tan x, right, all of these. And if I show you something like x equals pi on 2, there's one of our vertical asymptotes. If I instead say 3 pi on 2, there's another vertical asymptote. If I say negative, wait, that was weird. Negative 3 pi on 2, there's another vertical asymptote. At any of those like 90-degree angles, we have tangent is undefined. So you'll see it, if you approach from the left-hand side, it goes off to positive infinity. And if you approach from the right-hand side, it goes down to negative infinity. Cool. Why? Why? You want to ask these questions, why? I'm not going to answer that question. You can answer it for yourself. But if you do answer it, tell me that you answered it so I know you're thinking. All right, good. So we're also going to take a look in this lesson at solving exact and solving approximate situations. Let's go. Okay, so our first one. Sine squared x minus 1 equals 0. You could force the factorization of a difference of squares here, and that would be awkward. Easier is to not factorize, but just to add 1 to both sides. Usually we're going to want to set these things equal to 0 and solve them, but this one is simpler. So we're just going to add 1 to both sides. 2 sine squared x is equal to 1. So then we divide both sides by 2. Okay. And then we get sine squared x is equal to 1/2. And then we do a special move. We're going to take the square root of both sides. Is that correct? It's half correct. So what I need to remember here is to do plus or minus my solution so that I get both of the possibilities for sine x. So this tells me that sine x is equal to plus or minus 1 over the square root of 2. Now I think about my special triangles. Okay, and I'm thinking also about angles in standard position, and I'm like, well, you know what? I could put like pi on 4 there. Sorry, yeah, pi on 4. And that would be my 1 root 2 triangle, which gives me a sine of positive 1 on root 2. Okay, so that's pi on 4. Okay, or I could have this one over here where it's still 1 root 2 negative 1. That works as well because we're this one over that one for sine. Okay, so that's 3 pi by 4. And then we're going to also say, but we can also have negative, right? Sine could be negative here, negative root 2, that one there. And that angle, this angle here is 5 pi by 4. Why does it work? Well, this is root 2, this is negative 1, and negative 1 over root 2 is negative 1 over root 2. I mean, I don't know what to tell you. And of course, this one also works. All right, so we have that one's 7 pi by 4. Like that, okay? How do I know that? Well, I know that it's 1/4 pi less than 2 pi, so it's 7 pi by 4. Or you just count them. 1/4 pi, 2/4 pi, 3/4 pi, 4/4 pi, 5/4 pi, 6/4 pi, 7/4 pi, 8/4 pi. Every 45 degrees is a quarter pi. Okay, so then we could say x equals pi by 4, comma 3 pi by 4, comma 5 pi by 4, and 7 pi by 4. And those are your 4 solutions to this situation. Those are the exact solutions of x inside this interval. Okay, we have to give you an interval for problems like these. If we forget to, assume that it's 2 pi, 0 to 2 pi, one cycle of sine. Well, let's keep going. So, how about this one? Well, the difficulty just went up quite a bit, didn't it? Sure did. So, what do we do in this case? Well, what I would suggest is you turn this into something that looks a lot more familiar. So we're going to say let secant x equal, you can choose what you want. Let's call it a. All right? So then we would have 3a squared minus 5a minus 2 equals 0. I happen to know that this will factor if I do this. I decompose the middle term. How did I know that? I multiply 3 times minus 2 and I get 6, but it's negative. And then I want to add to minus 5, and those numbers are minus 6 and plus 1. Forget I saw any of that. Okay, so now I just go ahead and factor this. So this one factors by 3a multiplied by a minus 2 plus 1 times a minus 2 equals 0. That's factoring that and that by grouping. And then we group all this together. 3a plus 1 multiplied by a minus 2 equals 0. All right. So now what we can do is just solve both of these. So let's solve this one in black. A minus 2 equals 0. So that means a equals 2. So that means secant of x equals 2. Cool. All right. And then how about this one? 3a plus 1 equals 0. 3a equals minus 1. And a equals minus 1/3. So that tells me that secant of x equals minus 1/3. All right. Now, we want to go ahead and find all the values of x that make this true. Okay. We've got two possibilities. Secant x could be 2 because, well, how did I do that? I knew secant x was a. I decided that, so I move this down. This exact same logic happens here. All right. So if secant x equals 2, what is that telling me? Well, it tells me that cosine of x equals 1/2. Where does cosine equal 1/2, you say? Well, I think about this, and I think, well, cosine is positive over there, and it happens to be, oops, no, not there. I just get my special triangle right. Okay, so this is my 60-degree triangle, or my pi by 3. Okay, where this is 1 and this is 2, and that would give me, this is also 2 down here. So that gives me a ratio of 1/2. So that tells me that x equals pi by 3, or 1 pi by 3, 2 pi by 3, 3 pi by 3, sorry, I don't want to count it this way, is 1 pi less than 2 pi, so it's 5 pi by 3. 5 pi by 3 is equal to 300 degrees, and that's correct. Okay, so these are our two values for x that make this equation true. Okay, you could go back and plug that on a calculator and check it, and it will work because I'm so confident. Okay, but what about this next one down here? If secant x equaled negative 1/3, anyone getting heebie-jeebies? That tells me cosine x is the reciprocal of that. So that means cosine x is equal to negative 3, but this gives no solutions. Because this is outside the range for cosine. Cosine's never above 1. So that means secant is never between 1 and negative 1. Cool. All right. Now, how about this one? Well, again, I would suggest that you do a handy-dandy little substitution and say, let sine x be equal to, you can choose your own letter. You could choose your first initial. So I'm going to go g. Okay, so I have 2g squared minus g minus 1 equals 0. Okay, so this is the same thing. We want to multiply to minus 2 and add to minus 1. So that's 2g squared plus g minus 2g minus 1 equals 0. Okay, this first one factors into g times 2g plus 1. And this one factors into minus 1 times 2g plus 1 equals 0. Okay, and this factors into g minus 1 multiplied by 2g plus 1 equals 0. Okay. Two possible places to get our solutions over here. So we have 2g plus 1 equals 0. So that tells me g is equal to negative 1/2. So which is another way of saying sine x equals negative 1/2. So now I think about, okay, if sine is negative, that means it's down here in Q3 or Q4, all right? And where is sine 1/2? Well, it's for these like 30-degree ones, where that's 1 and that's 2. And this is 1 and that's 2. But the ones are negative, right? It's negative and negative, okay? So that happens to be pi on 6. This related acute angle is pi on 6. So it's pi on 6 more than pi. So that's 7 pi on 6. And this one is pi on 6 less than 2 pi. So that's 11 pi on 6. And those are both within this range. So that's good. Okay. And then how about this one? G minus 1 equals 0. Let's do it in another color. G minus 1 equals 0. G equals 1. So that is to say sine x equals 1. And there's actually only one place where that happens. That is, we visualize it up here at pi on 2, okay, where sine reaches its maximum. It only reaches its maximum once in the 360 degrees. It's a little bit like a parabola only having one vertex. Okay, not two solutions there. So that tells me x is equal to pi by 2. Done. And then circle it. There's your solutions. Okay, 3 solutions for that one. Cool, eh? So we get multiple solutions here. Both from the quadratic nature of the setup and the trigonometric nature. How about this one? If a quadratic trigonometric equation is non-factorable, we can still use quadratic formula. But here is where I would really recommend you use a substitution, okay? Because you'll get confused. You won't get confused. You might get confused. I might get confused. I could go ahead and write here cosine of x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. I could do that straight away. This is correct. But I would just encourage you to first go cosine of x is equal to v. Okay, it's a very popular substitution. Also happens to be one of your initials. Okay, so I could just put that there and then say v equals. All right, let's go. So if v equals that, so v equals negative b is negative 5 plus or minus the square root of 25 is 5 squared. Minus 4 times this times that is plus 12. All over 2 times this, which is 6. So we are v is equal to minus 5 plus or minus the square root of 37. 37 is prime. So this is gnarly nasty. Okay. Now you could back substitute in your cosine x, but we also want to consider how many solutions do we have. Because we're quadratic, we have like 2 potential sources of solutions before we go to the trigonometry, but we can exclude ones from our solution set if they exceed the range of cosine, right? If either of these is more than 1 or less than negative 1, then it doesn't give us solutions, does it? Of course not. No, and if you did, so we can write cosine x is equal to minus 5 plus or minus root 37 over 6. But minus 5 minus root 37 over 6 is absolutely less than minus 1. So only minus 5 plus root 37 over 6 provides valid solutions. Okay, so we eliminated half of our solutions there. Great news, everybody. So now we go cosine x is equal to, or we could even, yeah, we're going to do this. Cosine x is equal to minus 5 plus root 37 over 6. And so that tells us that x is equal to cosine inverse of minus 5 plus root 37 over 6. Okay, so now we go here to our calculator, change it to radian mode. All right, and then we're going to go just evaluate that. So 5, but it's negative plus 37, but I take its square root. Okay, equals, divide that by 6, equals, okay, this is the value of cosine, this is the cosine thing that we want. So it's very shy but positive, okay? So I'm imagining that that it's going to look something like this. It's going to be a very steep angle this way or a very deep angle that way, because cosine is positive over here. So we're going to have some angle there, and then I'm just going to minus that angle from 360 to get my second solution, okay? So when I do trigonometry, second function, cosine inverse on that. So it's 1.389 radians, okay? So that's a little bit less than half of pi, just like I predicted, okay? And so now I have this, so x equals 139, we'll just go to 2 decimal places, x equals 1.39, comma, or I can take this and take away that value from 2 pi, okay? How do I know that? Okay, I'm gonna draw a better diagram for you. Here. So I'm just thinking about my angles in standard position. I know that the value of cosine is positive because this thing is positive over here. Root 37 is bigger than minus 5. It's bigger than 6 even. So anyway, we are like over here because we're very, very close to half pi because cosine was very small. All right, this is a very small value. It's like a little bit bigger than 1 over 6. So that tells me that if this was like about 6, this would be about 1. So it's a very tall angle. That's how I know that. Okay, and then I also know that cosine is positive over here and over here. So I also know that the mirror angle also works, which if this is angle x, this is basically negative angle x. There, I just go backwards the same amount and I get the same cosine value. Okay, so how do I find that value of x, but within this interval? Well, I just have to walk backwards from 2 pi. Okay, I have to go backwards from 2 pi exactly x amount, and that will give that to me. So what I need to do is, because this is 2 pi, and this is in radians 1.39, I just do 2 pi minus 1.39. So that's why I can do that. Okay, so now I just take this number, and I am going to subtract 2 times pi. That equals that, but of course it's not negative because I did negative 1.39 plus 2 pi, and that would be the same thing as what I'm looking for. So our next one is 0.489. So Sorry, 4.89. And these would be our solutions to this equation. Happy? Yes, so these are the only two solutions. So we got 2 based on the trigonometric nature, and we eliminated 2, even though the quadratic suggests that there's 2 possible sources of solutions. Only one of them was valid because it was outside the range. Okay, try this one. Okay. Oh, look. Oh, would you look at that? So we actually want some coterminal angles in this case as well. I'm going to need to top up my coffee for this problem. I might even take a break and have a little fingerful of the icing of my cupcake. Just one sprinkle. Yeah. Just add I'm not going to do a substitution for this one. It's too easy. Add cosine to both sides. So we get 2 cosine of x plus root 3 equals 0. Just add cosine to both sides. Collect your like terms, right? And then subtract root 3 from both sides. 2 cosine of x equals negative root 3. And then what do you know? We just divide by 2. Cosine of x equals minus root 3 on 2. I should be able to give this problem to a grade 11. They should be able to solve it. This isn't too exciting. Even this doesn't make it that much more exciting. Well, we have to work in radians, so that's our big grade 12 trick. All right, cosine is negative. Okay, I know cosine is negative over there and over there. So we're looking for the minus root 3 on 2. So we recognize that we put our triangle this way. So where this one is root 3 but negative, this is 1 and this is 2. And we can also have the mirror triangle down there where this is minus 1. But we don't care about that because this is still, the hypotenuse is always positive. That's something I've been wanting to say the whole time. I feel like some of you are wondering, is the hypotenuse, why isn't that negative there? It's always positive. It's the distance from the origin. Distances are positive. Gently. Okay, so now we just go like cosine inverse of both of these. This one is, this angle here is pi on 6. So this is 5 pi on 6. And this one is 7 pi on 6. So x equals 5 pi on 6, comma 7 pi on 6. And if you're like, but Mr. Jennings, you're not done. You're right. There is also the solution 17 pi on 6 and 19 pi on 6. How did I know that? Okay, I want to go all the way up to 4 pi. 4 pi is the same thing as 24 on 6 pi. So 19 is less than 24, I think you'll agree. So I definitely need these two solutions. But how did I know they were there? I just use the period, right? I'm just going to add 2 pi to this one and get that one. Add 12 pi to the numerator, okay? And then I'm going to add 2 pi to that one and get that one. That's all. This is all you need to do, okay? You could also just like see it this way, right? Here we are, pi, 2 pi plus 5 pi on 6, 17 pi, plus another 1 2/6 of pi. Okay, and then we get to that one. You could visualize it too and go wee, wee, wee. Or you can just use my trick of just add the period. You just add 2 pi. This is so easy. Okay, let's keep going. I should hesitate to... Oh, look, the domain changed again. We have to consider negative values of x. Hooray! Okay, so we want to factor this one. So maybe we're going to do a substitution. Sine x equals... we've already used a... oh, I can't use e. I was going to use e. I'll use d. Okay, some initials in there. Okay, so we should say let, because this is like a move we're doing. Let sine x equal d. So we have 2d squared minus 3d plus 1 equals 0. We want to multiply to 2 and add to minus 3. Those numbers are minus 2 and minus 1. I think you'll agree that line is the same as the line above it. this factors as 2d times d minus 1 minus 1 times d minus 1 equals 0. So we know now 2d minus 1 multiplied by d minus 1 equals 0. I mean, you could resubstitute sine in that line, but I think that's gross. I don't know why you wouldn't just want to solve your two factors. So if d minus 1 equals 0, then d equals 0. And we know sine x equals 0. Cool. So there's one of our sources of solutions. And then this one, 2d minus 1 equals 0. 2d equals 1, and d equals 1/2. So that is to say sine x equals 1/2. There's another source of solutions. Now, consider where these things happen. Okay, so sine x equals 0, we're just going to pop up here and visualize this very quickly. It's there or there. Okay, it's flat. Okay, it has a y value of 0. It's on the x-axis, so it's 0 pi, or it is 1 pi. Okay, my hand is backwards. It's either 0 or it's 1 pi. Okay, so that's what you do. All right, so those would be, the solutions would be x equals 0 or pi or 2 pi, but also negative pi or negative 2 pi is also a solution, okay? Because we could do negative pi this way and be there, or negative 2 pi and be there. And it's all within the, see the equals, less than or equal to, less than or equal to? Yeah. Okay, so those are all good. Those are all valid solutions. All right, now what about sine x equals 1/2? Well, there we visualize our unit circle. We imagine that we have this triangle here where this is 1 and that's 2 and this is pi by 6. Okay, and we also know that, well, we would get the same triangle over here, or at least the same value of sine. That would be 1, that would be 2, and this would be negative root 3. But we don't care about the adjacent because the adjacent has to do with cosine. So we have pi by 6, so we have x equals pi by 6, 5 pi by 6, or what about negative 7 pi by 6? Or what about negative 11 pi by 6? Good, eh? Wow, we got a lot of solutions from that one. That's like, I don't know if I've solved questions with more solutions than that, but not ones that were this simple. Okay, so we had 5. So then for style points, you could list them all from smallest to largest. So x could equal minus 2 pi, comma, minus 11 pi by 6, comma, minus 7. That was 11 pi by 6? I turned my 11 into a pi. Weird. Minus 11. Imagine I lost a mark for that. Minus 7 pi by 6. Imagine you lost a mark for that. I'd take it too. I'd take a quarter probably. All right, 7 pi by 6. We also have negative pi. There's 0, comma, second line of solutions here. Next one is 5 pi by 6. Next one is pi, and the next one is 2 pi. Did I forget any of them? 1, 2, 3, 4, 5, 6, 7, 8. I feel like I did. Pi by 6. I'm missing pi by 6. Pi by 6. Okay, put pi by 6 here. Pi by 6 there, comma. All right, there's my big long set of solutions for x. I had 2 pages for that. Now, another strategy that you can use is like changing your period. So when you're, sorry, not a strategy, but like another way that these questions can get trickier is by changing the period. It can like increase the number of solutions you have or decrease the number of solutions you have. So let's take a look here at, ooh, yeah, that's just really hard to look at, isn't it? Yeah, so we're looking at sine x here. I'm going to zoom in a bit. Look at sine x. Okay, here. Oh, I zoomed in on like actually the screen there. So let's say we were told that like sine x equals root 3 on 2. Okay, and we can see we have a couple solutions there. Beautifully visualized for us. Okay, but what if I had instead sine 2x? Oh, look at that. By the time we get to 2 pi, we've already had 4 solutions at these places, okay? Oh my goodness, we changed the thing, okay? So there's some strategies that we can use to deal with these situations. All right, so one thing you can do is you can just like change the domain, and you can multiply the domain by the k value and then divide all the solutions by k. So if you had like sine x over this period, you could just solve like sine x over this period, and that will give you like your solutions as well. Okay. Okay, you can also just like figure out the period and make it work. So for like to determine how many solutions you will have. Like here, sine x has 2 solutions over 2 pi, but sine 4x has, 2 times 4, it's 8 solutions. And you get that, I get that by visualizing trigonometric equations, right? It's trigonometric functions here, see? Look at this. Even if I like limit my domain here, squiggle bracket, 0 is less than or equal to x is less than or equal to 2 pi. There. Okay, so there. So now we're just seeing one period of sine x, but you see we get 4 periods of sine 4x. So instead of 2 solutions, we get lots more solutions. So you get things like 19 pi on 2. That's cool. Pi on 12, yeah, you get pi on 12 as a solution. That's nice, that's neat. All right, cool. All right, great. Now let's keep going. Let's keep looking at this. So let's just do some examples. So cosine 2x is equal to 1/2. So in this case, I would just like, I would do it very algebraically like this. And this is what I'd encourage you to do. I'm messing around otherwise. So that would tell me like 2x is equal to cos inverse of 1/2. Okay, and then cos inverse of 1/2, well, we know that that is cosine is positive over there and over there, and 1/2 happens when this is 2 and this here is 1. Okay, so we are in our pi by 3 triangle, and we have this same one that's down here, okay, where this is 2 and this is still 1. Okay, so we are pi by 3 and 5 pi by 3. It's 1/3 pi less than 6 pi on 3. So that is to say 2x equals pi by 3 or 5 pi by 3. So then we just divide both sides by 2, right? We just have x is equal to pi on 6 or 5 pi on 6. Just divide both sides by 2, right? No, you're forgetting that you have more solutions. You're not forgetting. I'm not forgetting. I was doing that for dramatic effect. We have more solutions now because we just doubled the frequency. We squeezed the period, right? So now we have double our solutions. So what I would do is just look at this on a bigger domain. So our domain, we actually are interested in 0 up to, well, no, we're just I kind of don't understand what she's talking about. So we have this, and then we're just going to add 2 pi. So we would have 13 pi on 6. And then we're going to add 2 pi to that. So we're going to have or 17 pi. Aren't these lovely numbers? So many primes. 1, 5, 13, 17. We almost had a run of Fibonacci numbers there too. Because this one spins faster. So let's check our work in Desmos. Okay, this is going to really help your understanding of this stuff. So I'm just going to change this one to cosine of 2x, and we're actually interested in y is equal to, 1 on 2. This is what we're doing, right? Where am I? Yeah, cosine is 1/2. Cosine 2x is equal to 1/2, and we're going to find all the places where that's true. Okay, so let's see. So we have pi on 6, 5 pi on 6, 7 pi on 6, and 11 pi on 6. Of course I'm incorrect. Of course I'm incorrect because I added 2 pi and not 1 pi. Okay? And why does that make total sense? Because I want the domain to be in here, everybody. So that would be like just add, if I add 2 pi, I'm outside of that domain. That's silly. But also, when I add pi, because I'm multiplying that by 2 here, that is a full revolution. So instead, I have these ones, just add 1 pi to each. So this would be 7 pi on 6, and then this one would be 11 pi on 6. So let's check our answer again. Yes, 7 pi on 6 and 11 pi on 6. Hooray! Notice how checking a Desmos is a great learning experience. Learning 2. Add 1 error for Mr. Jennings. And here is a graph about like embarrassment versus happy. I'm not embarrassed, but I'm quite happy that I made that error. So I'm like over there, okay? Because it was a great opportunity for me to learn about this situation and avoid that error in the future. And I caught it because I checked my work in Desmos. You're allowed to do that when you practice, okay? So definitely practice and build your understanding with this stuff. Okay, let's keep going. I also have a cupcake waiting for me, so that's a good reason to do that. So here, divide both sides by 2, so you get sine 3x equals 1/2. And then we can go 3x is equal to sine inverse 1/2. And then this looks better when it's in brackets. And then when is sine 1/2? Well, I know that sine is positive up here and up here. And the 1/2 is my pi by 6 triangle and my 5 pi by 6 triangle. So this is pi by 6, and this is 5 pi by 6. Okay, so now I'm going to multiply both sides. So I have like 3x is equal to pi on 6 or 5 pi on 6. So now I divide both sides by 3. So that gives me x is equal to pi on 18 or 5 pi on 18. You know, maybe I should show this. If I divide 1/6 by 3, that's the same thing as keep, flip, change. So it's just multiply the denominator by 3, right? So that's where I get my 18s. So this is 1 on 18. Okay, so now I got my first 2 solutions, but I want to find the next 4. How do I know I'm going to get 6 solutions? Well, I find 2 solutions inside this little domain normally. That's for my solutions for 3x. But I'm going to get 3 times as many solutions, so I need 2 more. Now, how much do I need to add to each one? Let's see if I learned, okay? Because normally I would add 2 pi, but here I need to add 1/3 of that, okay? Because every time I add 2 pi by 3, when I multiply that by 3, I get 2 pi. It's 2 pi by 3. I was just a little too far there. So this would be there's 2 pi by 3, 4 pi by 3, and 6 pi by 3. So because there's 1, 2, 3 pieces, and I'm multiplying the speed at which this goes by 3, I can add 2 pi by 3 to each one of those and get my upcoming solutions. And I can do that twice to each one of them. So I can add 2 pi by 3 and I can add 4 pi by 3 to get there. So let's do that. So pi on 18 plus 2 pi by 3. Show you my fractions. This is the same thing as, well, 13 pi on 18. So it's pi on 18 plus 12 pi on 18. It's my common denominator. So that gives me 13 pi on 18. Lovely Fibonacci numbers. And then I'm going to add another 12 pi on 18 to 5 pi. So I get 17 pi on 18. And then I'm going to do it again. I might as well do it to here. Okay, so adding 12 to that is going to give me 25 pi on 18. And adding 12 to that gives me 29 pi on 18. And notice 2 pi would be 36 pi on 18. So these are the 6 solutions. Let's check my work in Desmos and see if I've got it. So we have here sine of 3x, and we want it to be equal to 1/2. We have there pi by 18, 5 pi by 18, 13 pi by 18, 17 pi by 18, 25 pi by 18, 29 pi by 18. Aren't mistakes lovely? They're lovely. Okay. So let's keep going. Okay, so here we want to solve this one. Tan 3x equals 1. So we have 3x equals tan inverse of 1. And when is tan 1? Well, tan is 1 over here. And sorry, tan is positive over there and over there. And it happens to be when this is 1 and that's 1, or when this is -1 and that's -1. In other words, that's pi by 4. And this one is 5 pi by 4. Okay, so we have 3x is equal to pi by 4 or 5 pi by 4. Divide both sides by 3 gives you x is equal to pi by 12 or 5 pi by 12. Now we are 3, right? So we can add some things to our solutions to go around the circle another time. If I increase x, so if I increase x by 2 on 3 pi, then I would multiply that by 3. So I'm actually increasing 3x by 2 pi. Watch. 3 times x plus 2 pi on 3 will be equal to 3x plus 2 pi. So that's how you add 2 pi, is you have to divide it there. Right? So I can add 2 pi on 3 to all of my solutions. So let's go. So, and I can do this, I can get 6 more solutions because I am tripling the number of solutions. So this one plus 2 pi on 3 gives me, well, we're adding 8, so we're 9 pi on 12. So watch. So pi on 12 plus 2 pi on 3 is equal to pi on 12 plus 8 pi on 12 is 9 pi on 12, which is a fancy way of saying 3/4 pi. Okay, so then we get 3 pi on 4, and then we add 8 to that one, and then we get 13 pi on 12. And then we're going to add 8 pi on 12, or 2/3 pi to this, 2/3 plus 3/4. Handy to go back to 9/12 here. So we are 17/12 pi. How did I know that? 3 pi on 4 is 9 pi on 12. 9 plus 8 is 17, because 2 pi on 3 is 8 pi on 12. Okay, and then we're going to add another to that. So that's going to be 22 pi on 12 when we do 13 plus, no, we're adding 8. We're adding 8. We're not adding 9. We're adding 8. So 13 plus 9 is 21 pi on 12. 21 pi on 12. So sorry, I'll write it out. I don't want to lose people over fractions. 13 pi on 12 plus 8 pi on 12. Beautiful Fibonacci stuff happening. 21 pi on 12, which is a fancy way of saying 7 pi on 4. There. So there's all of our solutions. Hey, do you think we should check this one in Desmos? Yeah, I'm not very good at visualizing trig functions myself because sinusoidal functions show up so much more often. So let's take a look. We are tan 3x equals 1. So we can even just write that in this way. Tan 3x equals 1. And it just gives us horizontal lines. All right, let's turn this off and that off, and we'll see where they are. It doesn't really tell us, but if I zoom in, there's pi on 12. There's 5 pi on 12. There's 3 pi on 4, which we had. There's 13 pi on 12. 7 pi on 12. And 7 pi on 4. And I think that was our last one. 7 pi on 4. Yeah, so they match. So you can also check it that way, just by type in the question and see what it says. Okay. Let's keep going. Okay, so cotan 3x is equal to root 3. I would turn this into tan 3x equals 1 on root 3, and then 3x equals tan inverse 1 on root 3. Okay, and then when does tan have a tangent of 1 on root 3? Well, it's positive, so we know that tangent is positive over here and back there. And it happens to be where this is 1 and this is root 3, right, on that triangle. And that's my pi by 6 triangle. And then this would be 7 pi by 6. Okay, so we know that 3x is equal to pi on 6 or 7 pi on 6. And because we have a 3 there, we want to get x is equal to pi on 18 or 7 pi on 18, but we want the boop, 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 more of them. Okay. Another thing we could do is right here, add your extra pi's. Just add your pi's there. So we're going to add 2 pi to this one. So we know we need 6 solutions. So add 2 pi to that, so that will be 13 pi by 6. And then add 2 pi to that one, so we're adding 12, so we're 19 pi by 6. And then we're going to add 2 pi to that one, so that's going to be 25 pi by 6. So we're adding 12 on 6 pi. And then this one, we add 12 to 19 is 31. And then divide all of these by 3. This is much easier. So this will be 13 pi on 18. This one will be 19 pi on 18. This one will be 25 pi on 18. None of these share any factors. I am checking to see if they can be reduced. 31 pi on 18. And of course they can't because they're mostly prime, or 25 is a square, but 18 doesn't have any factors 5. So do you think we're checking our work? Yeah, sure. Tan 3x. So we can write cotan. I think it will do cotan. Yeah, this should do cotan. Cotan of 3x. Cot 3x equals SQRT 3. Then we have to zoom out to see where our solutions lie. So this one is pi on 18. Oh, it doesn't really show me pi on 18, does it? That is indeed pi on 18. This one is, maybe it will if I do it this way. If I just write cot 3x, boop, like that. Let's just grab this, copy, put this down here, and then we're going to zoom out so we can see it nicely along its period. So this is the whole period of it. You can see the 3 solutions, and we're just going to type y equals SQRT3. And then that's a little higher than where I have it set. And so there, pi on 18, 7 pi on 18, 13 pi on 18, 19 pi on 18, 25 pi on 18, 31 pi on 18. Yay! More methods. Okay, so I like this method a little better. Well, actually, no, I like the first method that I was doing. It's more natural to me, but this, just like, I know I'm going to need 6 solutions, so I go ahead and add 2 pi. I go ahead and add 2 pi, and I do that enough times. I just like cycle through the period, bonk, 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 and then work it out. Do your practice, everybody. Get good at this stuff. Get good. All of these, like, you can find these in the D2L just by clicking on the hyperlink. You can also find lots of practice in the textbook, again, on the D2L. So I wish you well. Bye for now, everyone. Any questions, hit me up by email. Otherwise, have a great day. Oh, wait. I'm going to now take a bite of my well-earned cupcake. Worth that.